Welcome to Training with Frank. Frank Hack, master electrician and a developer of clean volt technology, shares his experience about wiring practices. Electricians, electrical shop foremen, and electrical engineers alike are amazed with Frank's knowledge base. Learn how to get the full intended lifespan out of all your electrical systems.
We already have an indication that energy surges decrease our efficiency. So we already know that capacitors only do one certain job, and that's what their job is. We know that TVSS technology cannot impact power quality. It's proven itself out to do that. So what do we do to cost effectively protect our system from energy surges at the same time improving power quality? Well, I harken back to the 1977 and 84 white papers. You need a surge device that is going to minimize the electrical surges to a point where you help bring your system to the normal level it's supposed to be. And the only way you can do that is by using a device that is going to be able to at least see the majority of the anomalies that ride in the area of the fundamental waveform that gets deviated the most. Clean volt, we developed Clean volt in the early 90s. First of all, as a catastrophic protection device. And we did so that it would, when it did fail in those circumstances, it failed safe. And what fail safe means, it didn't fail in a shorted condition. We are the only surge device that does not require our varistors to be fused because of that very thing called the fail safe. When our unit expires, it blows open, but what it does, it hangs on long enough so that the energy surge can be seen climbing on your main overcurrent device, allowing your main overcurrent device to see its overcapacity and shut down, just like that lightning arrestor and the cutout on the transformer. We can do that and facilitate that with one varistor per phase because there's no fusing. All the energy comes to the varistor that we make, which is a silicon carbide varistor. It's a seamless silicon carbide. It's patented. Okay? So basically in an electrical system, what does Clean Volt do? And that's the name of the product. We're going to take this, we'll call this a CDP because most of us are familiar with it. You usually have our one cabinet where we have our main overcurrent device. A lot of them, this is where your metering is. Some have a transfer switch. Oops, okay. And then whatever risers beyond that. So we'll make a two-riser system here. Okay. Everybody says, well, where do you put the protection? Well, why wouldn't you put it ahead of the system? Well, you put it ahead of the system, it's not going to help this here. It's going to help the overcurrent device ahead of it. Okay, usually it's a utility scenario. Secondly, Clean Volt is a device that's rated 750 volts or less. It cannot be ahead of the main overcurrent device of the system. It cannot be ahead of the meter. So let's say we got the incoming here. Normally then, the bus is down here. What we like to do is we put the unit on the riser or connected to the bus right in this area here. Because what happens is as a surge event, catastrophic surge event is coming in, it's going to pass through this main overcurrent device. It might be rated at 40 kA, it might be rated at 65 kA, 100 kA, and in the 480s, you can get as high as 200 kA. Whoops. Okay. And like all panels, we know that we do not put a branch circuit breaker downstream any less Ka rated than what the main overcurrent device is. Because what you do, if you put a 25 Ka rated device down here, the whole system is rated at 25 Ka. So you either put in the same Ka rating or higher onto your bus, okay, so to keep the Ka rating here. That's just a code requirement. But with Clean Volt sitting here, you have, and put on a 65 kA rated breaker, which would have to be, because let's say we're talking 65 kA. Surges, or energy surges, have time and distance. It takes time for the surge to come in and travel down the bus. Yes, there's this bus here. Everyone would think it would travel up that bus, but clean volt in the system now becomes the least path of resistance when it comes to energy surges. All those energy surges gravitate to the clean volt. So you would think that the surge would travel up there. No, it's traveling straight down to the clean volt. Even though it's connected to a 30 amp breaker, and this could be a 2000 amp breaker here, 2000 amp breaker here, the ampacity doesn't mean anything. It's all about the instantaneous current trying to enter the system. So while you might have 65 kA here, which is just about the limit before that breaker will trip out, time and distance shows that here you might only have 40 kA. So the clean volt is shunting all that energy into itself, and if it's a lightning type surge event, then it opens up like a shunt and drives it to the neutral ground. That's why it's good to have a well bonded neutral system. Allowing this to reach its maximum, and it literally turns it off. The surge is no longer coming into your building. Everybody says, well, it turns off the system. Well, isn't it better to have a system shut down that you can turn back on again, instead of having a system where all this surge energy after a TVSS has lost all of its varistors and allowing the rest of the surge to keep going? I mean, the surge is going to keep escaping on a TVS. It's just going to keep escaping into there. This thing is never going to see 65 kA. There's not enough power in a TVS. There's not enough of those, because they're going pop, 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 pop all the way along. In some instances, yes, TVSSs can protect the system, but I've not yet seen a TVSS shut down a main overcurrent device. Clean Volt has done it many times. This is where we started our protection. This is what Clean Volt was designed for, is protect the electrical system like the secondary surge arresters, the lightning arresters did on power poles, to give the system a chance to shut down. All right? That's the first line of defense. And that's basically how Clean Volt works, right there. That's its once again, its primary function. Now, over the years, and most of this started with customer feedback. And it wasn't anything I was looking for, but people were coming back and saying that they were seeing strange things happen. And they were saying things like, the power company came out and changed their meter. And well, why would they change the meter? Well, they think there was something wrong with the meter. And most of these scenarios happen to do with power factor. So I started investigating what's up with Clean Volt and why is it helping correct power factor. And it was only then that I determined, because we built the thing to clamp so low, in other words, within 10% of the RMS value, so 10% of RMS, without using Zener diodes. I'm not going to say you can't achieve that without Zener diodes. You can. But using a varistor, a very robust resistor that can literally absorb energy, and huge amounts of energy, and still act like a Zener diode, cleaning up the fundamental part of the waveform. How's that possible? It's because we clamp so low, 10% of the RMS. So let's take 600 volts. 10%, it's 660 volts. 660 volts. You have to remember the amplitude on 600 volts is going to be close over 900 volts. That's pretty serious protection. You know, so it doesn't matter what amplitude we're working with, as long as the unit is sized to the proper voltage, you're going to still see the same gleaning of the energy waveform. We don't worry about the voltage. There's nothing you can do about the voltage, deviating it. Okay? It's very, very difficult. I'm not going to say nothing, but you would have to put in incredible amounts of active power supplies and whatnot to be able to facilitate that, but then they wouldn't last very long either. You're basically taking AC, converting it to DC back to AC, but you still have the AC load on the other side reflecting back anyway. So you would still need something on, excuse me, on the load side of that active power supply anyway. So this is what CleanVolt facilitates, 660 volts. Clamping ability on the energy waveform. You can't do nothing with the voltage. We're working with my red. Okay, we're working with this guy. We're working with the current waveform. Anything this does, this mimics. So now we're reducing how the energy surges are and trying to clean up this waveform so it looks more normal. So when your equipment sees it, it greatly reduces that, what I call that oscillation of the piece of equipment. So it's got a smoother waveform to work with. The voltage, it's still going to be, voltage passes through as soon as it gets there. Now it's going to have a smoother current waveform to work with. That's what does the work, is the current waveform. So this impact, by doing this, it passes through the load easier. On a load itself, it's not being surged. It's not going to create more counter EMF. Therefore, less counter EMF coming back means the actual load now is acting, we talked about that 90% and 87%. Under really harsh conditions, it might be down at 80%. Brings it back closer to that 87% because it was already 3% underneath its own nameplate as it was. Okay, so that's what you get. That's fundamentally what you get when you put in the CleanVolt. You get this clamping ability. You get a catastrophic event protection unit that acts like a Zener diode. That's pretty powerful stuff. And because it's not fused, it has no limiting scenario. And when it comes to that, when we talk about time and speed, manufacturers of metal oxide varistors out there can tout, and maybe they can, is that their varistor, their MOV, has a reaction time. It can react to an event in less than 1 nanosecond, which is 1/1000th of a second. Pretty fast. There's transients out there that are that fast. There's no doubt about it. Okay? Problem is this is at the component level without the fuse. The fuse adds anywhere between 5 to 10 nanoseconds of speed reduction. And then you have the wire that's connected to the varistor. Okay, and then put the fuse here. Well, fuse there. We have that. Okay, every inch of number 14 T90 or number 14 T90 or whatever they use. They might use THN. Every one of them adds 1 nanosecond. Okay, a speed reduction. So before you know it, you've got a varistor that, number one, on its own clamps out of the range of the fundamental waveform. And its speed, by the time you hook it up, it's slowed down greatly from the advertised speed of 1 nanosecond at the component. CleanVolt, because it has no fusing. CleanVolt, because of its seamless carbon silicon carbide technology. And if you look at the periodic table, gentlemen, carbon is at this end, silicon is in this end. Two of the hardest components on the planet, opposite ends. We've married the two together and made it seamless. With 6-inch leads, our reaction time or action time, Acheon event, is less than 1 nanosecond. That's even before the component. 6 inches away from the component, we're less than 1 nanosecond. So at the component, we have incredible speed, but can't get to it because you still got to hook a wire to it. With 18-inch leads, It's 2.5 nanoseconds. We already know with TVSS technology, their fuse puts it between 5 and 10. So that's the kind of speed you're affording with CleanVolt. A catastrophic event protection device that has the ability to see the majority of energy surges being produced, acts like a Zener diode, and can protect you from catastrophic events with 18-inch leads. Mind you, we tell everyone when they're installing CleanVolt to keep the leads as short as possible, because the faster it acts, the better it is for everybody. But even with the 18-inch leads, we far outstrip any of the competitors at the component level because of their fuse. Now, when it comes to enhancing your power quality, CleanVolt is like any other system. When the capacitor company comes along, they tell you, they do their measurements and say, this is what you need. And you don't question them. You put it in. CleanVolt is the same way. We go out, we do an evaluation. We don't like doing anything minimum, but there is a minimum, and then if you so desire, you can build from there. What do you need to do? Well, let's take a multifaceted system, and it's going to call it main service, and it'll either be 600 or 480. Okay. You need a unit here. Protect your front end. Catastrophic protection. Okay. All your other stuff, all your other loads are going to be in probably, more than likely, distribution panels away from the main service. Depending on what you have and the distance from the main unit will depend on whether or not you need power quality protection at that point. Anytime you have a load that's heavy induction, a load that's heavy electronic, and we'll call that a light load, you definitely want to put something on here and something on here. Because you have to remember, you're policing the bus. Okay, you can look at this here line coming in as the major freeway. These guys, your secondary roads, the bus, and all the loads from here are like going off into your subdivisions. Okay? As long as you police the bus so that these guys are trafficked, so that nobody gets on at the same time, what you're literally doing here is making every connected device that's connected to a overcurrent device in that panel seem like it's working in its own world. We stop the interaction here. You don't stop it up here. This is where it's happening, right here. Okay? You got to keep it local. So reduce the interaction here. You don't have those energy surges, number one, being driven back into the system to recirculate through and recirculate through. You've stopped it here, and at the same time, it's no longer recirculating this way. You've stopped all that right here. You're giving a chance for your motor, your inductive load, to act like it's on its own and get back to its natural power factor. You're not allowing it to be surged by electronic devices, the harmonics being produced and that harmonic effect on causing those current surges. All those small current surges, which are affecting the top part of the waveform, are now being gleaned off. Now everything has a chance to settle down. You're policing everything. Then, from there, of course, you got your transformer. Like anything else. The utilities, when they drive out, they can drive out at 250,000 volts, 500,000 volts. The equipment that they use to protect it is at that voltage. When they go to a substation and step it down to 44,000, that 44,000 volt system now has its protection at its voltage level. And then you drive it down to 27, down to 8,000. All those voltages have equipment that's rated at those voltages for the protection of the equipment. You don't just expect the 250,000 volt equipment to protect the 8,000 volt equipment. No, it doesn't happen. Because what you've done is the transformer has broken the physical electrical connection first of all, and it's a different voltage. So if you step down from the 480 down to 208 into the panel here, then you have to start looking at putting the clean volt on just like you did this system here. It's a brand new electrical system. And drive it into the system for the power quality bump as needed. We've done a lot to alleviate people putting in capacitor banks to help increase power factor. I'm not saying that clean volt can take care of it all, but what clean volt is just like the foundation on your buildings. If you don't have a good foundation, that building is not going to last. So it doesn't matter whatever corrective measures you put into the system, unless it's properly protected to do the job they're designed to do, they're not going to be effective. Clean volt is the foundation of any good power quality management system, period. Without it, in my opinion, you're behind the 8 ball. TVSS technology will not afford you on its own this level of protection. If they want to drive down to get to an efficiency factor that clean volt does on its own, they have to use other components which are sensitive to energy surges that they cannot see because they clamp too high. So that's why these Zener diode boards and whatnot do not last. Do they do the job? Yes, they can do the job, but they don't last because there is no protection for them. The MOVs do not protect them because they clamp too high and they don't see the majority of the electrical anomalies. That's what you afford with clean volt, all in one unit. And then if you need extra capacitance, you put it where it's needed. You have to remember, once again, gentlemen, like I harkened back before, you do not want to take a motor and shove extra energy to it and expect it to operate properly. What you want to do is bring your system back to a new, natural level. And we've seen it done time and time and time again. I mean, we've taken people with 80 power factors up over 90. Case in point, in the year 2000, the Greater Toronto Airport Authority, their nerve center, 11 floors. Each floor had 200 amp service feeding all their computerized equipment and whatnot. And they had a huge, huge harmonic problem. And they finally got a hold of us through some chain of command. And once again, in those days, clean volt was going into the worst case scenario. We were always called up when everything didn't work. They were looking at putting in harmonically tuned transformers because they could, because their load, their nonlinear loads, their computer system, okay, their power supplies, had a constant harmonic order. I can't remember what it was, but it didn't change much. So they could put these harmonically tuned transformers in to facilitate and get rid of that harmonic or reduce it to a point where it wasn't burning stuff out. 20 grand a pop, and they couldn't shut down the power because the place runs 24/7, 365 days a year. We put in, on each panel, each 200 amp panel, we put in one of these guys. It reduced their harmonics by 18%. Problem solved. $20,000, over $1,600. Big savings, and they're still working today. That's the kind of protection clean volt affords you, all right? And harmonics are probably one of the hardest things to reduce. But once again, what was the problem? The problem wasn't the harmonics, it was the energy surges created by the harmonics being produced, deviating the fundamental voltage waveform, and all of those surge energies were hiccuping their power supplies and a constant resetting. I mean, their IT people were going crazy because of the problem. And it's a nerve center. I mean, it's a big airport. So what I'm trying to drive into everyone here is that clean volt is just not a secondary surge arrestor, okay? It's much, much, much more. You can replace so many different technologies. I mean, we're putting them on now. Instead of people putting in line-side reactors, we're putting in the clean volt because clean volt is shown to act almost like a reactor. People have asked us, is there capacitors in your little box? No. Are there diodes in your little box? No. Is it a reactor? No. It's a silicon carbide varistor that has the ability to glean the energy surges off the current waveform so it doesn't affect the equipment. Now, like Justin was saying, we're going back to the heat issue. Equipment that's already fatigued, there's not much that's going to help it. If it's fatigued heavy, it's already damaged. Not much is going to bring it back. I've seen fatigue panels where we've dropped the temperature some in the panel, but once it's fatigued that bad, I mean, your contact points in the breakers are already, past their point. Probably you have those microfractures on the bus. Clean volt can only do so much. I mean, even ourselves, like I said, clean volt cannot reverse damage in that type of scenario. It's not a human being. It can't do dishes, but at least allow you to do them because your dishwasher will stay up and running. Okay?